Who's shown up. Okay, so in the last lecture we sort of it ended abruptly. I was talking about elimination matrices, and so let's just complete that idea, even though I think we got the gist of it down. But so the idea was we're talking about elimination matrices, and so we made this one matrix to eliminate the x variable, or rather the first column entry from the second and the third row, right? So we were trying to get elimination matrices, and so let's do the same thing, but let's build elimination matrices for different row operations one by one. So let me call this row operation. Let's call this E1, let's call this E2, and let's call this E3. So I'm going to build elimination matrices to do these following row operations. So what I want is, let's say I want to do row 2 minus 2 row 1. So let me just write that in a different notation. So I want R2, the second row, minus 2 times row 1, right? So this is row 2 minus 2 times row 1. And so we saw how to build a matrix to do this elimination, and so the idea is we want to preserve. So the things that we would want to do is preserve the first row, and since we're only doing the row operation on row 2, we also want to preserve the third row as well, right? And so we saw, to preserve the first row, all we need to do is take a row which has 1 in the first column and then 0, 0, right? And so what this will do is take 1 of the first row, none of the second row, and none of the third row. This is also saying that you can also view matrix multiplication as sort of a linear combination of rows, right? And so, and to preserve the third row, what you do is you take none of the first row, none of the second row, and 1 times the third row. And you will see that if you do that, you will be able to preserve the first and the third row, right? So 1, 3, 2, let's augment this here, minus 2, and 3, 5, 6, minus 5, and 2, 6, 2, minus 2, right? And so if you do this matrix multiplication, you will notice that the first thing that you do is 1 times 1, 0 times 0, 0 times 0. So you get 1 here, then 3 here, 2 here, and minus 2, right? So if you do this matrix multiplication, and if you do the third row similarly, you'll just get the third row as it is, 3, 5, 6, minus 4. And so now the question is, how do I do row 2 minus 2 times row 1? And of course the answer is, so you're taking a linear combination of the rows, right? So you want 1 times the first row, so you put 1 in the second column, and you want negative 2 times the first row, and so you put, oops, not here, you put it 1 times here and minus 2 times here. And you don't want any contribution from the third row, so you just put a 0 here, right? And so now if I do this, it will be minus 2 times 1 plus 2, which is 0, minus 2 times 3, which is minus 6, plus 6, which is 0, minus 2 times 2, which is minus 4, plus 2 is minus 2, and then minus 2 times minus 2, which is 4, minus 2, which is 2, right? So this is the matrix that I get once I eliminate the second row, and let's just verify that that's exactly what we get. So 0, 0, minus 2. So there's an issue. We should have gotten 6 here. So let's see, minus 2 times minus 2 is 4, plus 2 is 6. Sorry. Minus 2 minus 2 is minus 4. Yeah. Am I getting 6? What's the issue here? So minus 2 times the first row is minus 4. Okay, minus 4 plus 2. So have I put in a wrong entry here somewhere? Minus 2. Oh, so the first entry was minus 3. This is the mistake. So that's the problem. And so minus 2 times minus 3 is 6. Minus 2 gives me 4. Okay. So that's the matrix we get. Shouldn't be minus 3. Yeah, you were absolutely right. I made a mistake there. Should have just checked the chat. Okay, so this is the elimination matrix. Let's call this E1, right? And so the elimination matrix that refers to row 2 minus 2 times row 1. And so you can build elimination matrices for row 3 times minus 3. And so E2 will be something like 1 0 0, you preserve the first row, 0 1 0, preserve the second row, and in the third row what you want is you want negative 3 times the first row, negative 3 times the first row, none of the second row, and 1 times the third row. And so if you multiply this with this, then you will get the second row operation. And finally you can do E3, which is preserve the first row, preserve the second row, and for the third row what you want is you want to take row 3 minus row 2. So 1 of the first row, sorry, of the third row, and negative 1 of the second row. So and so I'll get 0, minus 1, and 1. So the idea is if I multiply, if I take this matrix, if I call this A, right? Let's call this matrix A. Sorry about that. Throat seems to have an issue. Okay, so if I take E1 and multiply with A, and then I take E2 and then multiply it with the result, and then I multiply it further with E3, what I'm basically doing is I'm doing the row operations one by one. So this eliminates the first column entry in the second row, this eliminates the first column entry in the third row, and then this eliminates it in the third row, right? And so these are the elimination operations, right, that we do. Okay, one thing that we might be able to check is whether if we need a permutation matrix at some point, right? So let's see what the result is. So let's leave it here and let's see what we get. So we get 1 3 2, we have a minus 2 here, 0 0 minus 2 4, and so if I eliminate this I get minus 3, so this was 3 5 6 minus 5, right? I was multiplying it with the result. So this is E1 times A, right? So this was E1, this was A, and so E1A is this matrix. And now let's see what we get. So this is going to be E2 times E1 times A, right? So we preserve the first row, minus 2, preserve the second row, 0 0 minus 2 4, and for the third row we want minus 3 of the first row and then plus 3 times the first row. So minus 3 times 1 plus 3 gives me 0, minus 9 plus 5, minus 6 plus 6, and again I have seemed to be repeating the mistake. This is minus 3, minus 3. Okay, so this is minus 3. So minus 3 is 9, minus 5, which is 4. Now we see that at this point I shouldn't really be multiplying with E3 because I don't want to do this elimination. The problem is that I want to do an elimination. Actually, this is the wrong elimination to do at this point. What I want to do is that I see that the Gaussian elimination has failed at this point, and I want to save Gaussian elimination. And to save Gaussian elimination, what I would want to do is I would want to multiply it with a permutation matrix, which is I want to exchange these two rows, right? Exchange these two rows, and for that one I need a permutation matrix, and let's call that matrix P23, which is a permutation matrix which exchanges row 2 and 3, right? And so let's wonder what that permutation matrix would look like. So the permutation matrix that I want, if I want to interchange these two rows, I will of course leave the first row untouched, which means the first row needs to be preserved 1 0 0. For the second row, I don't want the second row, I want the third row. So instead I will put 0 here. I want none of the first row, none of the second row, but 1 times the third row. And again for the third row I want none of the first row, and if I want to swap it, that means I want 1 of the second row and then again none of the third row. And so this matrix multiplication, this P23 times E2 times E1 times A, will give me this matrix which has 1 3 2 minus 3 here, and then it will swap the rows 2 and 3. So I'll get 0 minus 4 0 4 here, and then 0 0 minus 2 4, right? And so that's the permutation matrix which swaps the rows that we want. Make sense? So these are called elimination matrices, and the idea is that the elimination matrices can actually be combined together. So this E2 times E1 can be written into, if we just multiply E2 times E1, we get a nice little matrix which does both the operations at the same time, right? So, and that's something that we built in the last class as well, which we built just directly. Over here I've built it separately, right? So E2 times E1. Okay, so that's the basic idea. There's also, in some books, in some notations, they use a different sort of notation. So where the second row and the first row is involved, they call it a row operation E12. Over here they call it E13, and in this one the row operation is or rather actually this is E21, E31 and E32. So this is the notation that they use for elimination matrices, right? So they're eliminating something in the second row using the first row. Over here we're eliminating something in the third row using the first row, and eliminating something in the third row using the second row. So that's the notation that's used. Okay? Alright, so that's all I want to say at this point about elimination matrices. Okay, let's move on and let's talk about a little bit about matrix multiplication, right? And this is something that we've assumed that I've assumed sort of that you already know, and we've sort of done a lot of matrix multiplication, but so far the ideas that we have gone through and the different views that we've taken give us a better picture of looking at different ways of looking at matrix multiplication, right? So if we just take a matrix, and let's take a nice little matrix. So this is, let's call this matrix A, and so initially if we just take this vector x, right? So this is 1 2 3 1 4 2 3 4 5 6 and 7 8 9. Let's just take this matrix, and this is some vector, right? x1 x2 x3. One way of viewing this matrix vector multiplication is of course to say that x1 times 1 4 7 plus x2 times 2 5 8 plus x3 times 3 6 9. So that gives you a column, right? So that gives you a column vector, let's say b1 b2 b3, right? That's one way of viewing a times x. Now what if we had to multiply? Let's take that view and let's extend it to not just matrix vector multiplication but to matrix multiplication. So this is B, and so let's say I have the same matrix 1 2 3 4 5 6 7 8 9, and let's say this B matrix had a few columns, right? So let's say this was column 1, this was column 2, this was column 3, right? So let's say I'm going to call these the columns of B. So this is column 1, column 2 and column 3, right? Okay, and so now what we're doing is, instead of looking at this as matrix multiplication, we can view it from the lens of matrix vector multiplication if we separate the columns of matrix B, right? And so the idea is that this matrix, if I just consider this column, then this matrix times this column is just a linear combinations of the columns of A given by the entries of B1. So if I write down the result A times B, the first column, so the first column that I get in this result, let's say, so this is a 3 by 3 matrix, this is a 3 by 3 matrix, and the result that I will get is also a 3 by 3 matrix. But the first row, let's call this row, right? This row over here, let's call this row A times B1, right? So what the first row of this matrix will be A B1, the second row will be A B2, the third row will be A times B3, and the idea is that we're basically doing matrix vector multiplication about the columns of matrix B, right? So AB1, let's just look at that one entry, which is A times B1, and let's say B1 was the column B11, B12 and B13. So A times B1 is basically B11 times the first column, which is 1 4 7, plus B12 times the second column, which is 2 5 8, plus B13 times the third column, which is 3, 6, 7, right? And so that's just AB1. And if we want AB2, then that's just B. So now this is a second column, so these entries will be different. But again, it will just be a linear combination of the columns of A. So instead of viewing matrix multiplication as going like doing the dot products, 1 times this, 2 times this, 3 times this, like taking the dot products of the rows and the columns, you can view it as a linear combination of the columns of A given by each of the columns of B, B1, B2, B3. So that's the first way. That's viewing it as, so if this matrix was AB, then the columns of A times B are linear combinations of columns of A, right? Okay. The other view of looking at matrix multiplication is something that we talked about when we were doing elimination matrices, right? So now let's talk about what happens if we look at them row by row. So let's shift the view and say, let's say, okay, so this is row 1 of P1, this is row 2 of P2, and this is row 3 of P3. And so let's look at this one, 4B6, 4, 5, 6. So this is 4, 5, 6. And remember, so if I look at it in the way that I was looking at elimination matrices, what is this row saying? This row is saying is that I take 4 times the first row, 5 times the second row, 6 times the third row, and then add them together, right? So this is saying that 4 times row 1. And so writing it in sort of, this is slightly weird to look at because the linear combinations are being taken row by row. So, but this is simply saying that you take 4 times row 1, plus 5 times row 2, plus 6 times row 3, right? And that will give you the second row of A times B, right? So if I look at the second row of A times B, so if this is A, this is B, oops, this is B, then AB, the second row of AB will be 4 times row 1 plus 5 times row 2 plus 6 times row 3, right? Just exactly like the way we were doing this elimination matrices, which so for example, this row said you take the first row, 1 times the first row, none of the second row, none of the third row, right? And that's exactly what's happening here. So what this is telling us is something different. It's telling us that the rows of A times B are linear combinations of the rows of B, right? So two different ways of looking at matrix multiplication. You either view it as a linear combination of the columns of A, or you view it as the linear combination of the rows of B. In this case, when you take the linear combination of the columns of A, the multiples, the scalar multiples are given by these column entries, B1, B11, B12, B13. And in this one, when you're taking the linear combination of the rows of B, then these entries 4, 5, 6 are given by, you know, the row entries of some particular row of A. Okay, so I can extend that argument and I can see that this is just, if this was 1, 2, 3, 7, 8, 9, then this first row was 1 times row 1 plus 2 times row 2 plus 6 times row 3, 3 times row 3, and this one would have been 7 times row 1 plus 8 times row 2 plus 9 times row 3. So these are just rows of AB. Okay, let's for a minute look at a large matrix. Let's look at a 5 by 5 matrix and let's build it in a special way. This is 2 5 by 5 matrices, and these are some entries. So this is some matrix B, and let's just label them according to rows. So this is B11, B12, B13, B14, B15, and so on. So this will be 21, 22, 23, 24, 25, and so on, right? So I'll change the first index tells me the row, and the second index tells me which column I am, right? So for example, this entry over here, this entry is in the 1, 2, 3, 4, fourth row and the third column, so this will be B, 4, 3, and so on, right? These are some of the entries of matrix B. Let's look at matrix A. Let's create a special matrix, and let's say, so this matrix gives me 1, 2, 3, 4. These are the first 4 entries. These entries are, let's say, 1, 1, 2, 2, 3, 3. This one is different. This is 2, 2, 2, right? So 0, 0, 0, 0, 0, 0. And this one is just 0, 0, 0, 0, 0, 0. Okay. And now notice that I've built this matrix in a special way. What I've done is actually instead of doing this, let me just put a I'm going to change this a little bit. I'm going to make this 0, 0, 0, 0, and I'm going to make this as, yeah, I really shouldn't have done that. Okay, let's do that. So this is 2, 2, 2, 0, 0, 0. Yeah, this is fine now. Okay, and so the idea is that I've constructed it in a way that I get some matrix patterns in some partitions, right? So if I look at this matrix A, I can divide it into different blocks. If I divide the rows along this line, partitioning, this is called partitioning a matrix, right? So I've divided it into 4 different blocks, and these 4 different blocks are actually quite, each of them have their own pattern, right? So this one, 1, 2, 3, 4, let's call this A1. Let's call this A2. A1 is a 2 by 2 matrix. A2 is a 2 by 3 matrix. Let's call this just, this is A3, but this is also just the 0 matrix. This is a 3 by 2 0 matrix. And let's call this A4, which is simply a diagonal matrix, right? So it only contains diagonal entries, which is sort of like reminds you of the identity matrix, but instead of taking just 1 times the first row, it takes 2 times the first row, 2 times the second row, 2 times the third row. So it's basically 2 times the identity matrix, sort of, right? And which is the 3 by 3 identity matrix, okay? And so now the idea is that if I want to do this matrix multiplication A times B, instead of doing A times B, let's also partition B into different blocks and get a nicer multiplication pattern, right? So now we write this as, we write A here. This is matrix A, which has been divided into 4 blocks, A1, A2, A3, A4. So I've just compressed this 5 by 5 matrix into a 2 by 2 block matrix, all right? So this is a block matrix. And I'll do the same for B as well. I'll do the same partitioning just to keep things simple. So this is, let's say, B1, B2, B3, B4, right? And so B1 is a 2 by 2 matrix, B2 is a 2 by 3 matrix, B3 is a 3 by 2 matrix, and B4 is a 3 by 3 matrix, right? And now if I want to do matrix multiplication, I can simply do the same thing that we do when we do matrix multiplication. And so block matrices, you can treat these blocks as entries, right? And so basically if you want the first row here, so this is, consider this a 2 by 2 matrix. This is a 2 by 2 matrix, which means the first entry over here will be what? It will be just, if I take the dot product, A1 times A2, A1 times B1, and A2 times B3, right? So I can view this as A1 B1 plus A2 B3. The other way, of course, of viewing this, so this is one way of looking at it when we look at it entry by entry. The other way of looking at it would, of course, be I take as linear combinations, right? So the first row of AB, right? If I want the first row of AB, then the first row of AB is basically going to be, the first column of AB is going to be the linear combination of the columns of A, which means this will be B1 times A1 A3 plus B3 times A2 A4, right? And the reason we do this is because some of these matrix multiplications are much easier to do than the others. For example, if I want to multiply, since A3 is a zero matrix, so for example, if this entry, let's look at this entry, right? So this entry will be A3 times B1 plus A4 times B2. I know that A3 is a zero matrix, which means zero matrix times any other matrix will be zero. So I can simplify this matrix multiplication by just doing this as A3 A4 times B2. I don't need the 0 times 0. So let me just write that. So when you're looking at the notes, this is just 0, so I don't need this term. I only need A4 B2. And similarly, A4 B2 is sort of like multiplying the identity matrix by another matrix, right? So I can view this as A4 times B2, but A4 is just 2 times the identity matrix times B2, and identity matrix multiplied by any other matrix is just that matrix. So this I can remove, and I can just say, so this entry will simply be 2 times B2. And so this matrix multiplication has been simplified by telling me that this block, this chunk over here, this entire chunk, if I take this, if the result is a 5 by 5 matrix, then I will have a, let's say this, so this is a 3 by 2 chunk, right? So there is a 3 by 2 chunk here, which is just 2 times, so this gives me 2 times B2, right? That's something that I can simplify my matrix as. So I can have a chunk here which is just 2 times B2. So this times this, and this times this. 3 by 2, 2 by 3, it's compatible, yeah. So that's a block that I will have right here. Okay. So this is called partitioning and block matrix multiplication. Right. Partitioning. And partitioning matrices can be, so block matrices can just be viewed as just matrices as long as the individual blocks are compatible for multiplication. So for example, let's check that some of these matrix multiplications that we've done are compatible. So A1 was 2 by 2 and B1 was 2 by 2, so that's a compatible matrix multiplication. A2 was 2 by 3, so A2 was 2 by 3 and B3 was 3 by 2, so that's a compatible matrix multiplication. And I think I've made a slight mistake here. This should have been B3, so this is B3, right? So try out this block matrix multiplication and see if you're getting the right result or not. Okay, all right, so that's matrix multiplication and different views. So we've got 3 different ways of doing it. So you view it as linear combinations of the columns of A, you view it as linear combination of the rows of B, or you do this block matrix partitioning and then multiply the different blocks together. So there's different ways of doing matrix multiplication. And the last way, the fourth way, of course, the fourth way is that something that you already know, which is viewing it as dot product of rows of A with columns of B, right? So the way we do that is just look at this as 1, 2, 3, 4 and 5, 6, 7, 8, and so the first entry is going to be the dot product of the row of A with the column of B. So the first row with the second column, which is 1, 2 times 5, 7, and the dot product is 1 times 5 plus 2 times 7, right? That gives me the first entry. Then the second entry is given by the dot product of this row with this column. So 1 times 6 plus 2 times 8, 3 times 5 plus 4 times 7, and 3 times 6 plus 4 times 8. And so that's another way of doing matrix multiplication. So now the question is, which way do you use? And of course the answer to that is whichever one is the most convenient for you at that, but for those 2 particular matrices. If you're working with column spaces or row spaces, then the idea is that you would want to view them as maybe the linear combination of columns or linear combination of rows, depending on whichever is easiest at that point. Okay. Right. And so this is now maybe the right time to talk about matrix inverses. Right? So what's the inverse of a matrix? And I assume that most of you would have seen 2x2 or 3x3 inverses, and let's just talk about what inverses are. And the basic idea is that if you have a matrix A, then the inverse of that matrix is called A minus 1, A raised to the power minus 1. This is simply a notation, but you read it as A times A inverse, you don't read it as A raised to the power minus 1. This is just notation. And the idea is, if I have a matrix A, then the inverse of that matrix is, when I multiply A with its inverse, I should get the identity matrix, right? And so this is matrix inverse we're only talking about right now. We're talking about square matrices, right? So we're talking about an n by n matrix. So A times A inverse gives me I. And the nice thing about inverses is, if the question is if inverse exists, then A times A inverse is equals to A inverse times A is equals to I. So even if you multiply it from the left hand side or you multiply it from the right hand side, you get the same result. You should know that in general, AB, if you take a matrix A times a matrix B, that's not going to be always equals to matrix B times matrix A, because the view is different. If you view it as a linear combinations of the columns of A, then this is a linear combination of columns of A, but this is now a linear combination of columns of B, right? Columns of B, and over here we have columns of A. So these are not in general going to be equal. So we say that matrix multiplication in general is not commutative. Is not commutative. And the idea of commutative is, of course, you know that xy is equals to yx. That's the commutative property of real numbers, that if I take 3 times 4 and I take 4 times 3, that's the same. But that's not true for matrix multiplication. So if you do A times B, that's not going to be in general equal to B times A. Sometimes it might happen. For example, if you take A times the identity matrix, then of course that's simply the matrix A, which is the same as taking I times the identity matrix times A. So you left multiply or you right multiply, doesn't matter, you get the same matrix. But for some general matrix, it's not going to be true. Okay. So commutativity doesn't really follow for all matrices. But if you have the inverses, then inverses are commutative, right? So if you take A times A inverse, that's going to be same as A inverse times A, and that's going to give you the identity matrix. So let's look at, but the big question is, does matrix inverse exist? That's the real question here, right? And let's talk about a matrix, right? So let's say I have 1 times 1, 2, or rather 1, 4, and 2, 8, right? Okay, so let's look at this matrix, and let's say I'm trying to find an inverse. This is matrix A, and this is matrix A inverse. I'm trying to find the inverse of this matrix is equals to, the result that I want is the identity matrix 1, 0, 0, 1. And those of you who know something about 2x2 matrices will immediately have seen that this matrix is not going to exist. I won't find the inverse of this matrix. But let's put that information aside. Let's not think about in terms of determinants, because I haven't even defined what determinants are. What I want to do is view this as a linear combination, right? And so think of it like this. Let's say I'm taking, this is A, B, C, D, right? And so I can view the columns of this identity matrix. I've already seen that I can see the columns of this matrix are going to be the linear combinations of columns of A, which means if I take A times 1, 2 plus C times 4, 8, that's going to give me the first column. So if I take linear combination with the first column of A inverse of these two columns, then that's going to be giving me the first column 1, 0, right? That's the idea. And the other thing that I get is if I take B times 1, 2 plus D times 4, 8 is equals to 0, 1, right? That's what I'm looking for, that some linear combination of them gives me 1, 0, some linear combination of these gives me 0, 1. But now let's look at the column picture, and the column picture is going to be extremely revealing at this point. So remember that we talked about that when you're taking the column pictures, you're saying that we're taking linear combinations of the columns of A. So if you view the column of A, so the first column is 1, 2, so let's make that vector, that's 1, 1, 2, so that's this matrix like this, so this vector, so that's the vector 1, A, struggling more than I thought I would, here we go, okay, so this is the vector, this is vector which has 1 in the first direction and 2 in the second direction, and if I draw the next vector, if I want to take linear combinations with this, so this is 4 times 8, and maybe I should have just drawn, given myself some more space. Okay, so 4, 5, 6, 7, 8, and so this is 1, 2, 3, 4, something like this. And if you notice that 4 times 4, 8, this vector is basically 4 times this vector 1, 2, which means that I'm just going to take this vector that I originally have, and this vector is just going to be now, it's just simply going to be scaled. Oops. So I take this vector and I paste it over here, and the idea is that this is just now going to be scaled such that it reaches that point, right? And if only that had been a nicer scaling, which did not happen. Oh well, never mind, let me just draw this vector as it is. So what happens is this vector gets multiplied with 4, right? So that's, now the problem is, if I want to take, what does this tells me? It tells me that these two vectors are in the same direction. The columns of A are going in the same direction, which means any linear combination of them is stuck in this line. I am not going to be able to get any linear combination that is outside this line, which means if I have any hope of getting 1, 0 and 0, 1, these vectors better be within this line. Otherwise, I can't take any linear combination of them to get 1, 0. And of course, that's a problem, right? Because 1, 0 vector is right here. It's outside this line. And the 0, 1 vector is also outside this line, which means there's no possible way I can combine these two column vectors and get two different vectors. This one is, even if I got 1, 0, I won't be able to get 0, 1 because it's in a completely different direction, right? So this tells me something, that column picture is telling me that I won't be able to find values A, B, C and D that give me this linear combination, and so I have no hope of finding the inverse matrix, right? And so this is telling me something which might come in handy later, which will probably come in handy later, but that is that if columns of A are in the same direction, then A inverse will not exist, right? And at this point I want to introduce a terminology that I have not used that far, but when we say that they're in the same direction, then we're going to use a term which is basically that the vectors are dependent, that they're linearly linearly dependent, right? And so linear dependence basically means that you can write one column. So linear dependence means that you can write one vector as a linear combination of the other vectors, right? So in this case we had 2 by 2. We had a 2 by 2 matrix, so we had only 2 vectors. But if we were working in a 3 by 3 matrix, then we would have 3 vectors which would each have 3 entries, and then the question would have been, are they on the line, or are they on the same plane, or do they cover the entire 3-dimensional space, right? And so let's look at the same answer, the same question now from the lens of a 3 by 3, right? So let's take a matrix A. This is 1, 2, 3, and this is 0, 4, 2, and this column is 1, 6, 5, right? So this is A. I want another, so I'm looking for A inverse, and I'm hoping to get this matrix such that I get 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm looking to find the inverse matrix, right? Now, of course, if I want this, let's say these entries are DEF, I don't know what they are, but I'm going to think about whether I have any hope of finding these 3 vectors, right? So let's view it in terms of linear combinations of A. So A, 1, 2, 3, plus B, 0, 4, 2, plus, sorry, not B, this is going to be D, plus G, 1, 6, 5. That's going to give me the first column of I, which is 1, 0, 0. Then the second column is going to be given to me by B, E, H, and the same vectors 1, 2, 3, plus 0, 4, 2, plus 1, 6, 5. And I'm hoping that I find some B, E, and H values that give me the vector 0, 1, 0. And finally, I'm looking for C, F, and I that give me plus 0, 4, 2, plus 1, 6, 5, and they give me this vector 0, 0, 1, right? And again, let's just one more time look at the column picture and see what are we really hoping for. So the first thing we're hoping, so we have a 3-dimensional space, and what I'm hoping is that the linear combinations of these 3 columns give me 3 different vectors. One vector is this, which is in this direction, 1, 0, 0. That's my first 1, 0, 0 vector. This is X, this is Y, this is Z. And I'm looking for a linear combination that gives me 3 different linear combinations that give me these 3 vectors. And now notice that these 3 vectors are the standard basis vectors, right? If I combine these 2, I can get to any point in the plane. And so these 3 are independent vectors. These are not in the same plane even, right? They're going in, this one is going in the X direction, this one is going in the Y direction, this one is going in the Z direction. So to be able to find these, to be able to make a linear combination of these 3 vectors into, so 1, 2, 3, 0, 4, 2, and 1, 6, 5, these better cover the entire 3-dimensional space, because these 3 vectors are in 3 different directions, right? They're not in the same plane. So if these 3 vectors, these columns of A, I need the columns of A must cover the entire R3, the 3-dimensional real space. And if that's not true, then I'm stuck. I won't be able to find A inverse. There's no way I'll be able to find these values A, B, C, D, E, F, G, H, I that gives me these 3 vectors. And if we view this, notice that this 1, 2, 3, these columns were specially constructed by me so that they don't cover the entire space, because if you notice, if you take this as C1, C2 and C3, then if you add C1 plus C2, then that's C3, right? Which means 1, 2, 3 plus 0, 4, 2 gives me this third vector 1, 6, 5, which means basically C3 is a linear combination of the first two columns, which means C3, C1, C2, C3, C1, C2, C3 are linearly dependent. And when they're linearly dependent, I'm going to be stuck in a plane, right? Because these two are in different direction, that is fine, because C2 is not a multiple of C1. So what I will get is I will get some planes. I'll get some two-dimensional plane. Let's say, let's make this some plane. So I get this two-dimensional plane in my three-dimensional space, but I won't be able to cover these three vectors in any way, because one of them or even two of them will be coming out of this plane, right? So there's no way that I'll be able to find some linear combination to give me all of these three vectors, which means I can say that if so this tells me that if columns of A are linearly dependent, then A inverse does not exist, right? As simple as that. Okay, right. And so that's the important fact, that if you look at it this way, that these are linearly independent, then here's something that you would want to think about. So let's look at, if I view them as columns, then these are linearly dependent, because 4 times 1, 2 gives me 4, 8. But notice that now I can look at this matrix if I look at it like this. So this is 1, 2, 4, 8. Now let's look at the same matrix row by row. And if I look at it row by row, then this is, the first row is 1, 4, and the second row is 2, 8. And these two rows are scalar multiples of each other, because if I take this row 1, 4, and if I multiply it by 2, I get 2 plus 4 and 8, right? Which means when the columns are linearly dependent, the rows are also going to be linearly dependent. And that's true because A inverse doesn't just exist on the right hand side. A inverse will exist on the left hand side as well. 1, 4, 2, 8. And if A inverse existed on the left hand side, each row of A inverse will take a linear combination of the rows of A. And the rows of A must also be linearly dependent, because the columns were linearly dependent. I know that the A inverse does not exist, which means the rows must also be linearly dependent. So this is easy to see in a 2 by 2 example for this one, that dependence of columns gives me dependence of rows. Let's see if we can check out how these two, so if I look at this 3 by 3, I've already seen that C1 plus C2 gives me C3. Let's see if we can say something about the rows. Let's see if we can find some linear combination in some linear dependence in the rows. So this is row 1, this is row 2, row 1, row 2, and this is row 3, right? Okay, so what can we do here? This is 1, 0, 1, this is 2, 4, 6, and 3, 2, 5, right? If I take row 3, so what can I do? I can take, let's say, so I say that C times row 1, some alpha times row 1, plus some beta times row 2 gives me row 3, right? That's my suggestion, that I say that alpha times row 1, which is alpha 0 alpha, plus beta times row 2, which is 2 beta plus 4 beta plus 6 beta gives me, I insist that this is going to give me the result 3, 2, 5, right? And so if I have this, then I can see that I can say that 4 times beta is equals to 2, which means it gives me beta is equals to half. That's one thing that I can do. And then alpha, then I can solve this equation, maybe alpha plus 2 times beta is equals to 3. So alpha plus 2 times half gives me 3. This is 2. So alpha is equals to 2. So let's try this out. So let's say I found alpha equals to 2 and beta is equals to half, right? So let's see if I can do that. So let's take alpha times row 1, so which is 2 times row 1 plus half times row 2. So 2 times row 1 gives me 2, 0, 2. That's 2 times row 1 plus half times row 2 gives me 1, 2 and 3. And if I add these two together, sure enough, I get 3, 2, 5. And so again, I've established that the rows of A are linearly dependent. That is, row 3 can be written as a linear combination of the rows of the first two rows. So again, the important thing to remember is that we've discovered an important fact, and the fact is that when, let's increase the font here, when the rows are linearly dependent, then the columns are also linearly dependent, and the inverse does not exist, right? That's the important fact here, that we won't be able to find the inverse of the matrix if you have linear dependence in the rows or in the columns of A. Okay? But here's a further question is, why do we really need the inverse? Why do I care so much about the inverse of the matrix? Why have I gone in such a detail? So what does the inverse guarantee? Or what does the inverse give us that we care about it, that we care about its existence or not? So let's look at it from the lens of the equation Ax equals to B, for example, right? If the inverse of this matrix existed, if let's say this is a square matrix, I'm assuming that A is n by n. If the inverse exists, then what do we get? We get, I can multiply A inverse on both sides. I can say A inverse times A x is equals to A inverse times B. By the way, when the inverse exists, it's a unique matrix. A matrix can't have multiple inverses. If it has an inverse, then that inverse is going to be a unique matrix, right? So A inverse times A gives me identity times x is equals to A inverse B, and the identity matrix multiplied by a vector gives me the same vector, so x is equals to A inverse B. And this gives me a nice little formula for solving the equation Ax equals to B. It's telling me that when the inverse exists, A inverse B, so Ax equals to B has a unique solution. That's the important thing, that it has a unique solution when the inverse exists. When the inverse doesn't exist, then we have some issues, but as long as we have some inverse, we can find a unique solution of the problem. So this is coming back to the question of linear systems, and you can relate it to the fact we can also say that it has a unique solution. Remember that Ax equals to B was also linked to Ax equals to 0. I asked this question at the end of, I think, the second lecture or the third lecture, which was, when does this have a unique solution? It has a unique solution when Ax equals to 0. Now again, A inverse exists, right? So I can multiply this by A inverse, x is equals to 0, sorry, A inverse times 0. On the left hand side you get x, on the right hand side you get 0. So this tells me that Ax equals to 0 has only the trivial solution. So we found some important facts, that when the inverse exists, then Ax equals to b has a unique solution. When the inverse exists, then Ax equals to 0 has a unique solution. Okay, so let's list these important facts down, and this is a list of equivalent statements that we will build. And so here's so let's say, let's change the color. So the first fact is Ax equals to b has a unique solution. Then that is the same as saying that Ax equals to 0 has only the trivial solution. Did I write it? Did I say that it has the trivial solution? Yeah. So it has the trivial solution, which basically means x is equals to 0. And this is true when the inverse of A exists. And this is true when the columns of A are linearly independent. And this is of course true if the columns are linearly independent and the rows of A are linearly independent. Right? So these are some facts that if one of them is true, all of them is true. If you find that the columns of A are linearly independent, so we're talking about the case when A is an n by n. So A is n by n matrix, and these facts, these are all true at the same time. Even if one of them, these are, let's call them equivalent. So these are equivalent statements, right? And the idea is if one of them is true, all of them are true. If one of them is false, none of them can be true, right? So if the inverse exists, then I know for sure that the columns are going to be linearly independent, the rows are going to be linearly independent. Ax equals to 0 is going to give me the trivial solution, and Ax equals to b is going to give me a unique solution. So this inverse of A exists. This existence guarantees to me a lot of these things, right? All of these facts follow just if we know that the inverse of A exists, right? Yeah, so that's the idea. Okay, so let's just state a few facts. Let's just talk about how do we know that the inverse of A exists or not, right? So we know that there's a couple of things that we know, that if Ax equals to 0 has only the trivial solution, then I know that the inverse of A exists, right? Another way of knowing that, how do we know? So how do we know A inverse exists, right? Any of these can be used to know that A inverse exists or not. Maybe this is not a nice way of finding out, but this, if Ax equals to 0 has a trivial solution, has only the trivial solution, then A inverse exists, which means sort of we know that this is not the trivial solution when there are free variables. So one property is that we know that there are no free variables, right? So, and when do we have no free variables? We have no free variables when we have n pivots during Gaussian elimination, right? So if we're able to find n pivots during Gaussian elimination, then I know for sure that I'm going to get A inverse, because I won't get any free variables. So let's talk about, let's say 1, 2, and 3, 4. Let's look at this simple matrix, and now let's apply some Gaussian elimination on it, right? So let's try Gaussian elimination. Okay, so if I do Gaussian elimination on this, I know that I need to do, this is simply, I can leave it like this, and the second thing that I can do is, so preserve the first row, and if I want to eliminate this entry, I do row 2 minus 3 times row 1, and the matrix for that is simply 1, 0, preserve the first row, and for the second row, take negative 3 of the first one and just 1 of the second one, right? So 3 times 4, and the result that I get is the following. So I get 1, 2, preserve the first row, and I get 3 minus 3 times 1, which is 0, and 4 minus 3 times 2, which is 4 minus 6, so I get minus 2. So Gaussian elimination tells me that I get 1, 2, 0, minus 2, and at this point I know that I have two pivots, 1 and minus 2. And this tells me that there are no free variables, and this also tells me that A inverse should exist, right? So how do I find A inverse? One way of finding A inverse is to try to solve this 1, 2, 3, 4. I know that if I multiply it with A inverse, I get 1, 0, 0, 1, right? So we're basically solving, so this is A, B, C, D, and if you think about it, you're basically solving two different systems. The first system that you're doing is 1, 2, 3, 4. Linear combination with AC is going to give you 1, 0. And the other system that you're solving is 1, 2, 3, 4 with BD is going to give you 0, 1, right? So this is AX1 equals B1. This is AX2 is equals to B2. So essentially what you're doing is you're trying to solve two systems at the same time which have the same matrix A, right? So this is just AX equals to B1, and this is AX equals to B2, and we're trying to solve X for both of these. Now one way of doing that is, of course, you solve them separately, do Gaussian elimination on this, Gaussian elimination on this, and stop. The other way of doing this, if you want to solve two systems or even multiple systems at the same time, you can do the same thing that we used to do, is use the augmented matrix. So 1, 2, 3, 4. Augment the first right hand side, which is 1, 0, and augment the second right hand side, which is 0, 1, right? And so now apply Gaussian elimination, and we're going to do Gaussian elimination, and we're going to go one step further from Gaussian elimination and do Gauss-Jordan elimination, and we'll see what Gauss-Jordan elimination is in a bit, right? So the idea is 1, 2, 3, 4, augmented it with 0, 1, 1, 0, 0, right? Okay, first row operation is row 2 minus 3 times row 1. So this gives me 1, 2, preserve the first row, 1, 0, and then 3 minus 3 gives me 0, 4 minus 6 gives me minus 2, 0 minus 3 gives me minus 3, and 1 minus 0 just gives me 1. Okay. Now at this point I could have stopped and I could have solved the systems, but I don't want to stop just yet. I want to carry this elimination further, and what I want to do is, now the first thing that I want to do, when I found all the pivots, I want to make all the pivots equals to 1, right? So the first pivot is already equal to 1. The second pivot I want to make equal to 1, which means I multiply row 2. So I multiply row 2 with minus 1 upon 2. So basically I'm dividing it by minus 2, right? And if I do that, what do I get? I get 1, 2, 1, 0. If I divide it by minus 2, then I get 0. Divide this by minus 2, I get 1. Divide this by minus 2, I get 3 upon 2. And divide this by minus 2, or rather multiply by minus 1 upon 2, I get minus 1 upon 2. This is going to be plus. Okay? That's the first thing I do. The second thing that I want to do is make all non-pivot elements equals to 0. So the pivot elements have become 1, and so the non-pivot elements, which is basically only this 2. By the way, when I'm talking about pivot elements and non-pivot elements, I'm only referring to A not to the augmented column. So I don't care about what's on the right hand side. This right hand side is good. I don't want to miss it. I'm just talking about this A matrix, right? And so this is of course no longer the same A matrix, it has been changed, but I'm only talking about the left side of the augmented matrix, right? Okay, so now the question is, how do I make this non-pivot element equals to 0? It's the same as saying that I want to eliminate this entry, right? And the way you eliminate some entry is to do the following. I can do row 1, so I have to add something in this, right? So row 1 minus 2 times row 2. And so let's try that out. So if I do row 1 minus 2 times row 2, I get 1 minus 0, so this is just 1. 2 times minus 2 is 0. 1 minus 2 times 3 upon 2, so this entry is 1 minus 2 times 3 upon 2, which is basically 1 minus 3, which is minus 2. So I can write this as minus 2. And 0 minus 2 times minus half, which is 2, 2 cancel, plus 2, so I get 2 over here. Okay? And so now this I can leave as it is, 0, 1, 3 by 2 minus half, right? And so at this point you see that you've actually solved the system. So let's look at this system first. Let's look at the first system we were solving. We were solving Ax equals to b1, right? And so let's write the system down. 1, 0, 0, 1. X was x1, x2 is equals to minus 2, 3 upon 2, right? That's the, I'm taking the first column and writing the system down, which I have simplified now. And the system has been simplified, and it actually, notice that when I turned it into this nice little matrix, which has actually become the identity matrix, you immediately get the solution. You get x2 is equals to 3 upon 2 and x1 equals to minus 2, right? So the first system that we were solving, this system that we were solving has the answers. What's the answer? The answer is minus 2 and 3 upon 2. So minus 2 and 3 upon 2. And the second one, notice that you can also get the answers to the second one, Ax equals to b2. It's just telling you that the first entry, x1, is going to be 2 and x2 is going to be minus half. So the second system that we were solving here is 2 and minus half. So 2 and minus half. So I take this, all this information that I have collected right now, take this and plug in the entries. So this was the information that I've collected. Oops. And let's just write this down. So 1, 2. So what does this tells me? This tells me that A is equals to minus 2, because this was the first system that we were solving, AC. C is equals to 3 upon 2. B is equals to 2 and D equals to minus half, which means A inverse is actually the matrix minus 2, 3 upon 2 and 2, right? And you can check that when you multiply A with A inverse, you will get the identity matrix. So this is A inverse. And notice that I did not need to go through all this trouble. At this point, even if I hadn't made this argument that I was solving this system, figuring out these values and then putting them back together, notice that when I built the inverse matrix from my information, it's actually this matrix I already had with me, and this matrix is right over here. Here it is, the same matrix. A inverse is right here, minus 2, 3 by 2, 2 and half, this matrix. So what happened was, when you take this matrix was A and this matrix was I. So when you augment matrix A with the identity matrix and you do Gauss-Jordan elimination, you get inverse the identity matrix here and A inverse here. So here's the final result. The result is that if we augment I to A and then apply Gauss-Jordan elimination. So Gauss-Jordan elimination was basically you first do Gaussian elimination, you get the n pivots, and once you get the n pivots, after this is the Gauss-Jordan elimination part of it, right? So the extra steps were the Gauss-Jordan elimination, which was basically make all the pivots first equals to 1 and then make the non-pivot elements equals to 0, right? So if we augment I to A and then apply Gauss-Jordan elimination on A augmented with I, then we get identity augmented with A inverse. So you can easily obtain the inverse of the matrix if you apply Gauss-Jordan elimination on this augmented matrices. So Gauss-Jordan basically converts this. If the left hand side is A and the right hand side is identity, if you apply Gauss-Jordan elimination, then this matrix converts into identity augmented with A inverse, right? So I've basically taught you two things at the same time. The first thing that I've taught you is how to apply. So the first thing that we have is that you can solve multiple systems at the same time by using Gauss-Jordan elimination and augmenting the augmenting all the right hand sides to the matrix A. So that's one thing that we did, right? We augmented all the right hand side that we needed. And the second thing that we've gotten is that Gauss-Jordan elimination on A augmented with I gives us I augmented with A inverse. Okay, so this is why Gauss-Jordan is important, is interesting, and it also gives you, for example, if we were solving two different systems, now let's extend this idea. If we were solving, let's say, if we were not solving for these two different right hand side, maybe this 1 0 and 0 1 was different. If I wasn't solving the inverse problem, then I could have just solved two systems, and the right hand side would have just given me the answers. For example, let's copy this. So let's slightly step away from the problem of the inverse. So we're not talking about the inverse anymore. So if I'm solving this system, right? So for the inverse, I knew that I had to find 1 0 0 1, but let's say that's not the problem that I'm solving. Let's say I'm solving two different systems, right? So this is sum x1 x2 and x1 x2, and I want to solve this for 1 3 and 4 8. Let's say that's the system that I want to solve. I don't know what this matrix is A, this x I don't know, and this other x I also don't know, right? So Ax equals B. These are the two systems that I want to solve. Again, you can solve this system by just starting off with 1 2 3 4, augmenting 1 3 4 8 over here, and now just using Gaussian elimination, or if you want to go one step further, use Gauss-Jordan elimination. So let's preserve the first row first, 1 2 1 4. For the second row, we want row 2 minus 3 times row 1, so this gives me 0, 4 minus 6 gives me minus 2, 3 minus 3 gives me 0, and 8 minus 12, right? So 8 minus 3 times this entry is going to be 8 minus 3 times 4, which is 8 minus 12, so this is minus 4. Okay, that's the first step. And now that you found all the pivots, what you do is you convert this into, you make this pivot 1, so this is 1 2 1 4, so you divide the second row, you multiply it by minus half, you get 0 1 0, minus 4 upon minus 2 gives me 2. That's you've made all the pivots equals to 1, and now we get rid of this non-pivot element by doing row 1 minus 2 times row 2. So 1 0, this one becomes 2 minus 2 is 0. Then I get 1 minus 0 is 1, and I get 4 minus 4 gives me 0. So the answer that I've gotten is the following. So the solution, this is the solution to first system, and this one is the solution to second system. So what I've gotten is that the first one, let's take these and let's copy this here. So what I've gotten is that the answer to the first problem is basically 1 times 0, and the answer to the second problem, the solution to the second problem, is 0 2. And again, you can immediately verify this because this was a very easy system to take. I made it deliberately to get a nice little answer, because if you view this in the column view, then it's just telling me that I take the 1 times the first column plus 0 times the second column. And of course, when you do that, you get the right hand side, the correct right hand side, which is 1 3 1 3. And if you take this one, then you're basically saying that take 0 times the first column and 2 times the second column, and of course that gives you the correct result, 4 8, right? So this was an easy system to solve. But multiple systems, what I've shown is that you can solve multiple systems using Gauss-Jordan elimination. And so these columns are basically, the columns are the solutions to Ax equals to B1 and Ax equals to B2. So that's, and of course these ideas carry forward if you want to look at 3 by 3 systems, right? So 1 2 3 4 5 6 7 8 9, and if you want to solve this Ax equals to B for different right hand side, let's say 1 2 3, or you want to solve it for 2 5 8, or you want to solve it for 9 18 27, right? You can solve this system by just taking, if I want to solve these 3 systems together, I just take 1 2 3 4 5 6 7 8 9 and augment all the right hand sides that I need. The first right hand side I need is 1 2 3, the second one I need is 2 5 8, the third one is 9 18 27, and then just apply Gauss-Jordan elimination. If you do that, if you manage to bring this matrix such that the left hand side becomes the identity matrix 0 0 0 1, then this will be the solution to the first one, this will be the solution to the second system, and this will be the solution to the third system. Okay, all right. I think I've conveyed most of what I wanted to do in this lecture. Let me just go through my notes. Okay, there is a couple of things that I will just like to mention here. There are a few facts. Another way of knowing whether the inverse exists, I talked about 2 ways of knowing if the inverse exists. The first one was that we don't have any free variables, or that you have n pivots during Gaussian elimination. Another way, if the inverse exists, then what you will have is that the determinant, something that you might be aware of, that the determinant of A is not equals to 0, right? And for, I think, 2 by 2 matrices you must have done that the determinant is simply these 2 entries minus these 2 entries, so 1.4 minus 2.3. So I know that 4 minus 6 is minus 2. This is of course not 0. That means A inverse exists, right? That's another way of telling whether the inverse exists. The other thing that I would want to mention, that if A inverse exists and B inverse exists, right, then if you want the inverse of the product, A, B, inverse, the inverse of the product, that you multiply them and now you are looking for, that is, you took A times B and now you're looking for a matrix that when you multiply with AB you get the same matrix, and that is equals to B inverse times A inverse. So if A inverse exists and B inverse exists, then AB inverse is equals to B inverse A inverse. And the reason for that is easy to see, that if you take AB and you multiply it by B inverse A inverse, then what do you get? The rule that I am going to use here is that matrix multiplication is associative, and this is a fact, right? That if you have 4 different matrices being multiplied, and if these two are being multiplied together and these two are being multiplied together and the result is being multiplied, it doesn't matter if you change the order of the parentheses. So you can write this as, so associativity basically means that A times B times C is the same as A times B times C. And so if you want to get rid of the parentheses, you can just write A, B, C. Doesn't matter in which order you do the multiplication, as long as multiplication is compatible. That is, the columns of this should be compatible with the rows of this, and the columns of this should be compatible with the rows of this. So if you use associativity on this product B inverse A inverse, then I can write this as A times B, B inverse, A inverse. Now B times B inverse of course gives me the identity matrix, and the identity matrix multiplied with any other matrix gives me just the same matrix. So A, I get A times A inverse, and again A is being multiplied by its own inverse, which means I get the identity matrix. So this combined result gives me the identity matrix. So basically what we've seen is that the inverse of AB is B inverse A inverse. So this matrix is AB inverse. Okay. All right, I think that's enough for today. We can go on, but I think most of you must be saturated by this point. I am definitely saturated. And yeah, let's limit the discussion up until this point, and we can carry this forward in the next class. Okay, so we've talked quite a bit in this lecture. What we talked about elimination matrices. We talked about the permutation matrix. We talked about how to view matrix multiplication in 4 different ways. You can view it as the linear combination of the columns of A, or the linear combination of the rows of B, or as this block matrix multiplication, or simply the way that you used to do in high school as dot products of the rows with the columns of, dot product of the rows of A with the columns of B, right? We also talked about the inverse existing. We talked about how can we know that the inverse exists or not, and the important fact is that the columns should be linearly independent, right? The columns and rows should be linearly independent, because if they're dependent, then we won't have the inverse existing. We also said that if the inverse existed, the Ax equals to B will have a unique solution, Ax equals to 0 will also have a unique solution. In particular, this solution will be the trivial solution. So these are equivalent conditions. And then we looked at a specific way of computing the inverse. How do we compute the inverse? You just augment it with the identity matrix. You do Gauss-Jordan elimination, and the matrix that you find on the right hand side is just the inverse matrix. Okay. Alright, and of course Gauss-Jordan elimination can be used to solve multiple systems at the same time. So if you want to solve for this right hand side and this right hand side, just plug this one here, first one here, second one here, do Gauss-Jordan elimination, and the solution will be this, right? Okay, and the same thing goes for 3x3 matrices, and of course all of this we've talked about holds for any n by n system. You can have it for 2x2, 3x3, 4x4, so on and so forth. Okay, so I think we've covered up until at least, I believe, 2.5 of the book. Let me just see if there's anything that I've missed out on. I don't think that I have. And so 2.5 is also something that we've covered. From the next lecture, we'll look at do we have a 2.6? Yeah, so factorization. So LU factorization is something that we'll look at in the next class. Okay. All right, that's it from my end. Let me know if you have any questions. So next class we'll do LU factorization.